Hello everyone, welcome to another episode for Learning Electronics. In this video, I'm gonna talk about some rules that we have to consider when we want to design a circuit and we want to use capacitors. So I want to talk about capacitors in circuit designing. So let's get started. First of all, I want to talk about, in a nutshell, about the capacitors and introduce you and say some features about capacitors. So, what is a capacitor? A capacitor is a passive element in electrical circuit that stores electrical energy in an electric field. Capacitors consist of two conductive plates separated by an isolator or dielectric. The primary function of capacitors in circuits are energy storage and release, voltage smoothing, and creating time delays. Types of capacitors: ceramic capacitors, small and economical, high stability. Applications: filters, smoothing circuits, and high frequency circuits. Electrolytic capacitor, high capacitance compared to other types. Polarized. Applications: power supply circuits, voltage filters. Tantalum capacitor, more stable than electrolytic capacitors. A small size with high capacitance. Applications: digital circuits, power supplies. Film capacitor or polyester or film, high capacitance and voltage, high stability and long lifespan. Applications: high power circuits. Mica capacitors, high thermal and frequency stability. Applications: precision circuits and high frequency circuits. Now I want to talk about important points for circuit design with capacitors. Capacitance selection. The first step in choosing a capacitor is determining its capacitance. Capacitance should be selected based on the need of the circuit for energy storage, signal filtering, or frequency tuning. Example: for filtering ripple in power supplies, high capacitance capacitors like electrolytic are used. Working voltage. The capacitor's rated voltage should be higher than the maximum operating voltage of the circuit to prevent damage or explosion. Tip: always provide a safety margin, for example 20% above the circuit's maximum voltage. The next one, capacitor type. The type of capacitor is chosen based on the circuit's application. For high-frequency or RF circuits, ceramic or mica capacitors are more suitable. For energy storage or filtering, electrolytic or tantalum capacitors are used. Polarity. Some capacitors, like electrolytic and tantalum, are polarized and must be placed correctly in the circuit. Reversing these capacitors may cause damage. Next one, ESR or equivalent series resistance. ESR impacts the performance of capacitors, especially at high frequencies. Capacitors with low ESR are better for power filters and switching circuits. Pay attention. Tip: in switching power supply circuits, choose capacitors with low ESR to minimize voltage ripple. Temperature and frequency stability. Some capacitors, like ceramic, vary significantly with temperature and frequency changes. For circuits requiring high stability, like timer and oscillators, use capacitors with high stability, like mica or polyester. Physical size and shape. The size of the capacitor should match the available space on the PCB and circuit applications. Higher capacitance capacitors are usually larger and may take up significant space. Leakage current. In sensitive circuits, the leakage current of a capacitor, especially in electrolytic and tantalum types, can be problematic. In such cases, use capacitors with a low leakage current, like ceramic capacitors. Next one, ESL or equivalent series inductance. In very high frequency circuits, ESL can affect the capacitor's performance. For such applications, use capacitors with low ESL. Practical applications. Filtering. Capacitors can remove voltage ripple in power supplies. Timing. In timer circuits, capacitors and resistors can set delay times. Resonance circuits. Capacitors are used with inductors in resonance circuit to tune the frequency. Now move on for say something in details. Capacitance rating. The main formula for this is Q equals C cross V, that Q is charge stored, C is capacitance in farads, and V is the voltage across the capacitor. If the capacitor is used for filtering, for example in power supply, higher capacitance values, for example 100 microfarad to 1000 microfarad for low voltage, are typically suitable. For timers and oscillators where timing accuracy is important, smaller capacitance values such as nano or picofarads are used. Please note that in high frequency circuits, selecting the correct capacitance is crucial to avoid voltage drop and ripple. Rated voltage. Key point. The rated voltage of the capacitor should be at least 20 to 30% higher than the capacitance working voltage to account for transient voltage change and improve stability against electrical shocks. For example, if your circuit voltage is 5 volt, use a capacitor with a 10 volt rating. ESR. ESR, as I mentioned before, is the internal resistance of the capacitor in series with its capacitance. This parameter is especially important at high frequencies, as it reduces the efficiency of the capacitors in switching circuit. Practical note. For DC to DC switching circuit and circuits requiring fast filtering, capacitors with low ESR such as ceramic capacitors should be used. Electrolytic capacitors generally have high ESR and are better suited for lower voltage filtering and low frequency applications. ESL or equivalent series inductance. As I mentioned before, at high frequencies, both ESR and ESL come into play, reducing the capacitor's efficiency. Capacitors with high ESL cannot store and discharge energy effectively at high frequencies. For RF circuits or fast digital circuits operating at high frequencies, capacitors with low ESL, such as MLCC or multi-layer ceramic capacitor, are suitable. Leakage current. Some capacitors, such as electrolytic capacitors, have leakage currents over time, which can cause problems in voltage-sensitive or timing-sensitive circuits. For precise circuits and analog signals, use capacitors with very low leakage current, such as ceramic or polyester film capacitors. Temperature and frequency effects. Ceramic capacitors exhibit significant changes in capacitance with varying temperatures and frequencies. For timers or oscillators requiring high stability, use capacitors with an NPO temperature class, which minimizes capacitance change with temperature. For high-frequency circuits, capacitors with good stability at high frequencies, such as mica or film capacitors, are recommended. Polarity. Electrolytic and tantalum ceramic capacitors are polarized. Be sure to connect their positive and negative terminals correctly as reverse connection can lead to failure or even explosion. Non-polarized capacitors such as ceramic, film, and mica can be used in either direction. Ripple current. The maximum ripple current the capacitor can handle must be greater than the circuit's ripple current. This is especially important in switching power supply circuits, which higher ripple current can cause heating and damage the capacitor. Stability and lifespan. Electrolytic capacitors have a limited lifespan and may fail in high temperature conditions or after several years of use. In such cases, use capacitors with longer lifespans such as film capacitors. Bypass and decoupling capacitors. In digital circuits, bypass or decoupling capacitors are commonly used to eliminate voltage noise and smooth the power supply. These capacitors are usually placed close to sensitive components such as microcontrollers or ICs to filter out voltage noise. Bypass capacitor size. Typically, 0.1 microfarad to 1 microfarad ceramic capacitors are used for digital circuits. Physical layout on PCB. The placement of capacitors on the PCB is important. Bypass capacitors should be placed close to the power pins of sensitive components for optimal performance. Also, the trace between the capacitors and load should be short to reduce the inductance effect. Now, I want to give you an example about circuit design when we use a capacitor. Suppose you want to design a switching power supply circuit to filter the output ripple voltage using electrolytic capacitors with low ESR and high capacitance, for example 470 microfarad or more. At the input of power supply, place a 100 nanofarad ceramic capacitor to remove high frequency noise. For sensitive digital circuits such as a microcontroller, use a 0.1 microfarad ceramic bypass capacitor near the power pins. So in this video, I talked about some rules and some tips that we have to consider when we want to use capacitor in designing an electronic circuit. So if you have any other points or tips, please leave a comment and share your knowledge to us and your friends and who watch this video. Thank you for watching. Please give me a thumbs up and please introduce our channel to who likes to learn electronics. To the next video, take care, see you soon, and bye bye.